Namaste. In this video, we shall understand the fundamentals of vernier calipers intuitively, and we shall derive the formula that you use to find a measurement taken by the vernier calipers. However, by understanding the fundamentals or the basics of vernier calipers, you should also be able to have the intuitive understanding behind screw gauge and spherometer, because all these three instruments are based on the same principle of mechanical interpolability. What is mechanical interpolability? That is, for example, if we take an object A, B, and we coincide the zero of our scale with the end A, and then the end B falls within 2 marks. Let's say it's mark 1 and mark 2, between 2 marks of the scale. Then we do an interpolation to find out uh, to which mark the end B is closer, and depending on that, we approximate the end B to coincide with either of these 2 marks, correct? So if that is the case, okay, then it involves a little bit of human error, because someone could visually find the end B to be closer to end 2 and the mark 2, and someone could find B to be closer to mark 1. It little bit depends on human error, because there are no sub markings between 1 and 2. To reduce such human errors, the instruments like vernier caliper, screw gauge, and spherometer, these were invented. And what they do, they use mechanical interpolability based on certain mathematical calculations, which we are going to understand intuitively. However, there is one more thing also. This is called visual acuity, which is a term that you need to, or a phrase that you need to be acquainted with. Visual acuity. And this could come as a question in your lab or practical exam. So, visual acuity is the ability of a human being or someone to use his vision to resolve the distance between distance of a particular point between 2 marks on a scale. So based on the principle of visual acuity, we have the three instruments like vernier caliper, then we also have screw gauge, and we also have spherometer. So they all three operate on the same principle. So let us try to understand vernier calipers and derive the formula, and almost on the same principle, you can also understand screw gauge and spherometer. Wouldn't be a big problem. So let's have a simulation of the vernier caliper. So look at this vernier caliper. There is no error, so it's an error-free vernier caliper, and there are no objects at the top. The upper jaws are there, at the bottom the lower jaws are there. So why do we use vernier caliper? We use vernier calipers to measure the external or internal diameters of cylindrical objects, right? So for external, there is the lower jaws. For internal, there are the upper jaws. Right, so that's what we use the vernier calipers for. Let's get back to the simulation again. So when the zero of the vernier caliper, okay, here again, let me remind you that the upper scale is called the main scale, which is basically a centimeter scale or a millimeter scale. The lower scale, the one that can slide, that is a vernier scale. Okay, and if we look closer, what happens when there is no object or no measurement being done? It's a zeroth setting, error-free zeroth setting. In that case, let us just zoom into the this particular section. Let me just zoom in and let's try to understand here what happens, what's going on. So let's just snip this thing out and put it on our notepad. Okay. And let us enlarge this thing. Okay. Now you see that there are 10 divisions on the vernier scale. This is the vernier scale and this is the main scale. This is the main scale, this is the vernier scale. So there are 10 divisions on the vernier scale, and there are and these 10 divisions on the vernier scale equal to the 9 divisions on the main scale. So we can write the equation here like 10 vernier divisions equal to 9 main divisions. So how much is one vernier division? So one vernier division is 9 upon 10 of main division, which is 0.9 main division. So if we let me highlight, use blue ink here. So this each of these gaps or divisions equal to 0.9 main division, and since one main scale division or main division is 1 millimeter, so each such division is 0.9 millimeter. Okay, not even 1 millimeter, 0.9 millimeter. However, there is one more thing that we can also find out. Let's use a little bit of our brain and see and enlarge this image. If I enlarge this image even further, I would see that focus on this part of the first division on the vernier scale. This is the first division. See, there is a slight gap between the first division of the vernier scale and the first division on the main scale. That this particular gap we can also find out, calculate, because we know that this but entire division is 1 millimeter, and from the previous calculation or the last calculation we did, we know that this is 0.9 millimeter. So we know this tiny gap. This is exactly the principle of mechanical interpolability that we talked about. So let's just get back to our calculations. We know that the small gap or the first gap, let me change the ink. The first or the first gap, if this is the first mark on the vernier scale, then let me define that the first gap or the first right gap, because the gap is to the right, the first right gap, or which is the first RG at the first mark on the vernier scale is equal to 1 millimeter, which is the main scale division, minus 0.9 millimeter, which is the vernier division. That gives me 0.1 mm, and that's the first right gap. So that means it's 0 of the main coincides with the 0 of the vernier. Now the first on the main does not coincide with the first of the vernier, so this particular gap to the right, okay, of the first mark on the vernier scale is our first right gap, and that is 0.1 mm, which we call the least count. LC, least count. Least count is a concept which we define as the minimum amount of measurement that can be accurately done by any measuring instrument. Okay, so let me write this down. Least count is considered as the minimum amount, of measurement that can be accurately done by any measuring instrument or the measuring instrument at hand. So that's the least count. That means we know that the first right gap on the vernier scale equals to 0.1 mm, and that is the least that we can measure accurately. We know, we are very sure, because if there is no error on the device, there is no zero error. That means when there are zero objects inside the jaws, so and that means the zero of the main and the zero of the vernier, they coincide, then the first right gap will be the same as the least count, which is 0.1 mm. And in this case, we see that two markings on vernier scale coincide with the main scale. One is 0, one is the mark 10. Okay, that means if we displace the vernier scale to the right, because it cannot slide to the left anymore, so if we slide it to the right and make sure that the 0 does not coincide with any of the markings on the main scale, then the 10 will not also coincide with any of the markings on the main scale, because the 0 and the 10 they both follow the same trend. Okay, if 0 coincides, then 10 will definitely coincide with some markings. Okay, however, if neither 0 nor 10 coincide, then there will be at least one mark on the vernier scale that will have the best alignment with the main scale markings. Okay, so it could be exact alignment with the main scale marking, and it might not be an exact alignment with the main scale marking. Okay, uh, that is why you need to use your visual acuity to find out which marking on the vernier scale has the best alignment with the main scale markings. Okay, now that is this alignment thing, the coincidence of the vernier markings with the main scale markings does have a really important purpose in finding out the actual measurement. Why? To find that, let us again enlarge this image, and okay, let me just rather copy this once more and paste it on another page and try to understand how this happens. Okay, so now look at this. Here the 0 coincides with the 0, that means the 10 coincides with the 10 on the vernier scale. That is the vernier scale. Okay, this is the vernier scale. I write it as V, and the upper scale is I write it as M. Now let me change the ink, and we know the right gap. This right gap is is one list count. Okay, let's just call it a list count, one list count. So when we repeat the same process, okay, zero, this particular division is fixed, so each division on the vernier scale is equal. However, the right gap, the first right gap, compare the first right gap with the second right gap. Okay, so what happens is, if the first right gap is one list count, then the second right gap will be two list counts. Why? Because again, from we start at 0, we cover one vernier division. Okay, so this main division is one vernier division plus one list count, and from there this division, okay, from there this division is two vernier divisions plus one list count, and this is again one the if see, if this mark, the first mark coincided with the first mark of the main, then this would have been just one list count. However, this goes to the left by one list count. That means there is already one list count, and because this mark goes one list count to the left, we have two list counts here. So this is one list count, this is two list counts, and similarly this will be three list counts, and this will be four list counts. Okay, so, and on the 10th mark it will be 10 list counts, 10 list counts. And since one list count, let me go create some space. Now since one list count is 0.1 mm, so at the 10th mark there will be 10 list counts. The 10th right gap will be 10 list counts, which will be 0.1 mm times 10, that is 1 mm. So you see the right gap, 10th right gap is exactly 1 mm. So we say that there is no gap because it exactly coincides with one of the marks on the main scale. So imagine that if we put some object within the jaws, or we expand the jaws to fit some gap, and the and the and one of the marks on the vernier division coincides with one of the marks on the main scale, that means that particular mark has moved has covered the gap it previously had with the nearest marking on the vernier division, correct? And depending on how much that mark has moved, whatever mark 4 moves, or the distance moved by any mark on the vernier division is the same as the distance moved by the 0th mark on the vernier division, because the vernier scale does not expand, right? So that is why we let us understand this by a practical example. Let's do the simulation again, and in this case let us put an object. Okay, so let's say that I put an object between the lower jaws, and then that gave me something like this. Let's say something like this. Okay, so now let us try to focus how much reading has been covered. To focus, let us take a screenshot of this part. Okay, now let's expand again, try to understand what has happened. Now the 0th mark on the vernier scale has moved for sure. We are definite about what the 0th mark has gone beyond the first mark. In fact, it has gone beyond 1.1, 1.2. So it is 1.2 on the main scale. So definitely the object has a diameter that is at least 1.2, what do we call 1.2 millimeters. Okay, not 1.2, 1.2 centimeters actually. It will write this very clearly, 1.2 centimeters, because this is basically a centimeter scale. 1 centimeter is 10 mm. So 1.2 centimeter is basically 12 millimeters. But then let's call it just 1.2 cm. Now the next mark is 1.3 cm. So whatever the diameter is, so the diameter is greater than 1.2 and is less than 1.3. So this particular gap, okay, the left gap is something that we need to find out. Okay, what we need to find out by using the Vernier caliper here is this particular gap, which otherwise we would have to assume or use interpolation or visual acuity to just approximate whether it is closer to 1.2 or 1.3. So if we do not wish to do rough approximation and we want to find a much more precise and accurate measurement, then we also have to consider how much this gap is. To find how much this gap is moved by, we need to find one of the marks on the vernier division that has the best alignment with one of the main scale markings. And from this, we see that this particular mark, the seventh mark, is having the best possible alignment here. That means this, had this not have happened, had the zero of the vernier division coincided with, let's say, 1.2 marks, 1.2 marking of the main scale division, then everything would have become just like that, like we discussed in this case. Okay, very similar, but that is not the case. The zero has actually moved. In this case, the zero has moved by this gap. Let me mention that gap in red, the left gap. Okay, this is the gap. The zero has moved. That means all the markings have moved by the same amount. However, the seventh marking aligns with one of the main scale markings. The seventh marking on the vernier scale is aligned with one of the markings on the main scale. It doesn't matter which marking is it on the main scale. What matters is which marking on the vernier scale coincides. Because if it coincides with one of the markings, that means it has covered the 7 list counts. Okay, because seventh marking was beyond, how much was the right gap for the seventh marking? It was 7 LC was the right gap of the seventh right gap. Seventh RG was 7 LC, right? So if it now coincides, that means it has covered 7 list counts. Okay, and that is the same distance that has that has been covered by the zeroth mark on the vernier scale. So this left gap of the zeroth mark is the same, okay, as the right gap on the seventh. So the zeroth left gap is the same as seventh right gap, which is 7 list counts. So we can find now every time we use such instruments, all we are interested in is the zeroth left gap. Okay, especially when there is no zero error involved. That means the device does not have any alignment error when there is no measurement. So zeroth LG, or the zeroth left gap, is the same as seventh right gap, which is 7 LC. So instead of 7, it could be like the first marking could be having the best alignment, or the second, or the third, or fourth. So for nth right gap would be n times LC. Okay. In this case, it is the seventh, but it could be any, n could take any value between 1 to, not 10, 1 to 9. Okay, because if it is 10, then it will definitely, the 0 and the 10 will definitely coincide, and then the 0 will also coincide. But then if 0 and 10 coincide, then there is no issues. We don't even have to look at the vernier caliper and do any calculations, because we know exactly from the main scale the length of the object, or the diameter of the object. So it is between 1 to 9 where we need to use the formula. So the nth gap, okay, nth right gap is what we need to find, so that we understand what is the zeroth left gap, which I have marked in red here. Okay, so this is what we need to understand, and that is n times LC. In this case, it is 7, so it is 7 times list count. List count is 0.1 mm, right? So 0.1 mm, which is 0. Since LC is 0.1 mm, which is the same as 0.01 centimeter. Now we have the zeroth left gap. We need to understand zeroth left gap. Okay, and I repeat that when I say the gap, it is basically the distance between a mark on the vernier division or the vernier scale, the gap between any particular marking on the vernier scale and the nearest mark on the main scale. Okay, so when we talk about the left gap, you need to go in the go leftwards. When we talk about the right gap, you need to go rightwards. Okay, so depending on that, you need to find out. So now we understand how much this distance is. We know for sure that the object is of length 1.2 cm. The object is of length 1.2 cm. Now, but it is for sure this much, but there is something extra, which is the zeroth left gap. We need to add a zeroth left gap, which is 7 times LC, that is 1.2 cm plus 0.07 cm, that gives you 1.27 cm. So this is how you find the the length, okay, depending on what is the value of depending on which marking on the vernier scale coincides with or properly aligns or have or has the best alignment with one of the markings on the main scale. Okay, because if it is the nth marking that has the best alignment with one of the markings on the main scale, then the nth marking has covered n times least count, okay, when we have done the measurement. Initially it was n times least count behind the respective marking on the main scale, but now since it aligns with the main scale, then it has covered the n times the least count. That means since this particular marking, nth marking on the vernier scale has covered n times least count, the zeroth marking has also moved by the same amount, which is the n times least count. So the left gap of the zero is determined according to that. However, from this you can also find out if the left gap, if the zeroth left gap is given to be x, right? Then this zeroth right gap, how would you find? You know that the left gap plus the right gap is one vernier division, one main scale division, which is 1 mm. That means the right gap will be 1 minus LG, 1 minus the left gap. So in this case, in this particular case, we know that the 7th division on the vernier scale has moved. Okay, that means it has covered 7 times least count. That means the zeroth left gap is 0.7 mm. So the zeroth right gap will be 1 minus 0.7. So it is going to be 1 minus 0.7, which is 0.3 mm. Why is this important? The right gap, it is important when we talk about negative zero error. We will talk about that soon. So now let's move on to the zero errors. Okay, we have understood uh, the list count, the concept of the list count. We have understood the concept of alignment. We have understood the concept of the gaps. Okay, now we need to understand the concept of zero errors. Okay, now let us look at the zero errors. Let's reset our caliper and let us let's take the zero error to be positive. Okay, I let's take the zero error to be 1 2 3. Okay, I have take let's take make it 5. Okay, so let's say that by default there is some manufacturing error with this instrument, and for that, when I try to close the jaws of this vernier calipers, what happens is we're now talking about errors. Okay, let me enlarge this. So when there are no objects, the still we know that the zero of the main scale does not coincide with the zero of the vernier scale, which ideally should, but due to some manufacturing error with this instrument, this is not the case. In that case, we know that by default this much of error gets added to every measurement that we make on this instrument. Okay, so that means we can easily find out how much this is, because this is the zeroth left gap, and how much is the zeroth left gap. We can find out the best alignment on the vernier scale, which is let's see this one. Okay, this one, which is the 5th marking. That means the zeroth left gap is 5 times least count. That means the let's write in black. So the zeroth left gap is 5 times least count, which is 0.5 mm, and that is the positive zero error, or let's call this delta plus. Delta plus is positive zero error. Okay, zero error means when there is the measurement is zero, there is some error, and that is positive, which is plus 0.5 mm. Now let us do some corrections. Let's call that correction as C. Let's say the correction, let's call the correction C. Sorry. The purpose of correction is that to by adding the correction, we have to make the net error as 0. That means delta plus C has to be 0, since delta plus is 0.5 mm plus C is 0, gives us C is to be minus 0.5 mm. So we have to add a negative correction. Whenever the zero error is positive, we have to add the correction which is negative, so that the net error comes as 0, right? So this is the concept of the error correction in case of positive zero errors. So whatever the measurement you get, you just add the negative of the zero error, negative of the magnitude of the positive zero error, or the negative of the positive zero error, to find the actual measurement in the case where the device or the vernier caliper or the screw gauge or the spherometer has some positive zero error. However, the trickiest part is when we have negative zero error. That is why I explained you the left gap and the right gap logic. So let us again look at the simulation. This time I will make the -5. Let me make the zero error as -5. Okay. So in that case, let us again take a screenshot of this. Okay. Uh, got some issues. Let's copy it again and paste it. Okay. Now, in this case, look at this. It's really important because questions in JEE Advanced are based on negative zero errors, mostly not on positive zero errors. Try to understand this. This is when the negative zero error happens. You see, in case of negative zero error, the at the zeroth measurement position, the zero of the let me switch to red again. The zero of the vernier scale is to the left of the zero of the main scale. So this is the error now. Okay, but then let's, if we go to the positive zero error thing, what did we measure? If that is okay in the previous one. Okay, hold on, let me delete this one. Okay, this is the positive one. Okay, in case of the positive zero error, we took the left gap. Okay, we measured the left gap. But in the negative zero error, we are talking about the right gap. Okay, of course the error is negative here, but we are also measuring the right gap. So the vernier, by vernier coincidence, the vernier, imagine that there is some mark here. Okay, zero. If it is zero, imagine there is a mark on the main scale, that is, let's say, whatever it is, a negative marking. If it is zero, then it has to be a negative marking. But then we are only considering the left gap. However, we can calculate on the basis of the coincidence logic. We can find the left gap, and then we can subtract the left gap from one division, and then we find the right gap. So let us find the zeroth right gap in this case. So zeroth right gap, zeroth right gap in this case is equal to 1 minus, again 1, I say 1 division on the main scale is 1 mm, minus, find the best alignment. Which is the best alignment here? It is the fifth mark on the Vernier scale that is giving us the best alignment. So it is 5 times list count, which is 5 LC, which is 1 minus 0.5. What is that? Millimeters. Okay, so this is 0.5 mm. So when it is the right gap for zero errors, it is the negative right gap. So if that is the case, how much are we having the error? It is the zeroth error is the delta minus, which is minus of 0.5 mm. Now see, every measurement, basically the zero of the Vernier scale has gone to the left of the zero of the main scale. That means it has reduced. It should be zero, but the measurement is negative 0.5 mm. That means every measurement done by this faulty instrument gives us a reading that is 0.5 mm less negative than the actual measurement. So to have zero correction, to have net error as zero, we need to find delta minus plus some correction gives us zero. That implies correction is 0 minus delta minus, which is 0 minus of minus 0.5 mm in this case, which is plus 0.5 mm. So for negative zero corrections, we get positive result. Okay, whenever we have to correct a negative zero error, we have to add the negative of the negative zero error. It is always negative of the zero error. Okay, if it the correction has to be negative of the zero error. If the zero error is positive, the correction will be negative. If the zero error is negative, the correction will be positive. However, when the zero error is negative, always remember this, when the zero error is negative, you are actually measuring the right gap. So but the correction needs to be based on the left gap. That means for negative zero errors, you always have to find your error from the left gap logic, not from the right gap logic. And as I said, the for nth for you need to remember this, for negative zero errors, for negative zero error, if the nth Vernier mark, Vernier mark gives the best alignment, gives the best alignment, gives the best alignment, then the zero error or delta minus is 1 minus NLC in mm. 1 minus NLC mm, where LC is the least count, which is 0.1 mm. Okay, so remember this thing, that for the negative zero error, that is the case. However, for positive zero errors, when there is a, this is the same thing for the screw gauge as well as for the spherometer. When there is positive zero errors, if the nth Vernier marking gives the best alignment, then delta plus is simply the what do you call NLC. However, there is one important thing you need to understand, that when we talk about zero errors, it should be like that. Let's go back to the simulation. Okay, the zero, it's not like, for example, if I take a positive zero error of let's say 4, then the zero of the Vernier scale has actually moved a little bit slightly. This zero error has to be very small. You cannot have this as a you cannot, if you think like this particular gap is is kind of an error, then that is not an error. You cannot have, for example, if I close this and the maximum error that I can have is like 9, the 0 has to be between the 0th mark of the main scale and the first mark on the main scale. The 0 must lie between that for the formula of zero errors that we have found. Okay, so I mean that is reasonable. If you see, if the zero error, if I cannot make it more than 9 or minus 9. Okay, so the 0 has to lie between the 0th and the first mark on either side, on left or right. The 0 has to lie between them. It cannot go like the 0 cannot go like this. It cannot go, this cannot be a zero error. Okay, if this is the zero error, then the instrument must be discarded almost immediately. It's a health hazard, it's a mental health hazard. All right, so that part should be taken as understood. I believe that this has helped you understand the basic formula behind the instrument. So it's needless to say that any measurement done on a vernier caliper, you just have to find the what is the main scale reading. You find the main scale reading, a main scale reading MSR, plus the vernier. What we found is the left gap, which is the vernier reading, right? Plus the vernier reading, vernier scale reading VSR, plus or minus delta, which is the zero error. If it is plus delta, it has to be negative zero error. If it is negative delta, it is positive. So the actual reading, this is the actual reading, is the main scale reading plus the vernier scale reading plus or minus the zero error. If the zero error is 0, then it's just main scale reading and vernier scale reading. I believe that has helped you. And if you think that has been useful, so let me know in the comments, subscribe to the channel. And if you have any further doubts on in physics, then you can reach me and discuss with me in the answers forum on my own blog. I'll give you the link in the description. It is thephysicist.in/ask. Thank you very much.